Hallo, it's dumplet here. Here's an item on algebra. Find the sum of all possible real numbers b such that x squared plus bx minus 3b is equal to 0 has integer roots. Credits to the Philippine Mathematical Olympiad for this item. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Alright, now here we do have b to be a real number, but some of you guys might realize, well, we do have integer roots, so if I were to factor this expression on the left hand side, well, that I should be able to factor into two factors with integer roots, obviously, and that's going to give me b to be an integer. And yes, your instincts are correct, but we could kind of prove this with just a simple fact. The sum of the roots via the Vieta's formula, it's going to be negative b. Now we know that the roots are two integers, so we're saying that the sum of two integers is negative b, and that's pretty much enough for us to say that b is an integer, right? So that's going to tell us that b is an integer, and this is actually very interesting because we could apply this in the green condition, the quadratic equation having integer roots, because that's going to mean that the discriminant is a perfect square, right? Now why is that so? Now, obviously, b squared plus 12b in the discriminant. Oh, by the way, we get this from the quadratic formula. So solving the roots via the quadratic formula, I'll get that the discriminant is b squared plus 12b. Now, obviously, b is an integer, so the discriminant is an integer. And in this case, if the discriminant is not a perfect square, then obviously this one, the radical, it's a radical, so it's going to be irrational. So it's going to be irrational, which is going to cause this entire thing to be irrational. But we know that's not true because the roots are integers. So that's going to be enough for us to say that the discriminant is a perfect square. So we could write this as b squared plus 12b being equal to a certain perfect square, let's just say k squared. And let's just assume without loss of generality that the square root is non-negative, okay? So essentially, we just have this Diophantine equation in integers, obviously. So b and k are integers, and we have a lot of techniques to solve. But in this case, we do have a square. We do have two squares. So let's try to complete this square. Maybe some factoring would work. So b squared plus 12b, completing the square here. I'm going to add 36 to both sides of the equation. That's going to give me, on the left side here, this becomes the square of b plus 6. I could put the k squared on the other side, minus k squared, then 36 on the right hand side, and as mentioned, factoring here apparently because we do have a difference of two square scenario. So typically whenever you see perfect squares or squares generally in a Diophantine equation, maybe the difference of squares would be used. So try to complete the square and you might be able to observe something nice such as this one. Anyways, moving on, factoring will give me this as the first factor and this as the second factor, and then they have a product of 36. And because b and k are integers, we could just do the method of assigning of factors, which is pretty nice. All right, so we do have these two factors, and because we set k to be a non-negative integer, that's going to be enough for us to say that the left factor is less than or equal to the right factor. Now, there's another thing we could try to do. Let me just try to take the sum of the two factors we have here, the left factor and the right factor. They actually add up to 2b plus 12. So the sum of the two factors is even. 2b plus 12 is even. So that's going to mean that the two factors are either both odd or both even. Now we could eliminate the both odd case because obviously odd number times an odd number is an odd number, so it cannot be 36. So it must be the case that our two factors are both even. So we just have to kind of incorporate the factoring here. We must find two numbers multiplying to 36, and the two factors, they must be both even. Now, doing some listing here, it's going to give me 2 and 18, and then 6 and 6. So we must have the condition that the left factor is less than or equal to the right factor. Now, obviously, b and k are integers here, so it is possible that b is negative, so we must also incorporate the negative factors. So just negate the first and the second pair, so it's negative 6, and the other pair, negative 18, negative 2. Now I switched them kind of because I have to maintain this condition. The left factor is less than or equal to the right factor. Now, since I did notice that the sum of the factors is just 2b plus 12, it would be very nice for us to just simply add the two factors and then solve for b, because b is the value that we want. So the first case, 2 and 18, they add up to 20. Second case, they add up to 12. Third case, they add up to negative 12. Fourth case, they add up to negative 20. And I could just solve for b in the four equations. In the first one, I'll get b equals 4. Second one, I'll get b equals 0. Third one, I'll get b equals negative 12. And then the fourth one here, I'll get b equals negative 16. Now, obviously, you could always put the b back and check if k is an integer as well. So in the first one, I will get that k here would be 8. In the second one, I'll get k is equal to 0. In the third one, I'll also get k equals 0. And then in the fourth one over here, I'll get k equals 8 again. So k is an integer for all four cases of b. So let's just take 4, 0, negative 12, and negative 16, add them up. So 4 plus 0 plus negative 16 plus negative 12, that's going to equal negative 24. And this will be our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!